This is the second video on Introduction to Robot Design in VEX parts, and the next thing we're going to talk a little bit about is center of gravity, or center, also referred to sometimes as center of mass. So this little X here refers to where the center of mass might be on these four different robots here. And in general, for stability, usually lower is better, and more closer to the middle is better, unless you have, sometimes if you have high traction wheels on one side but not on the other, then you'd want your center of mass on the high traction wheels so that you have more weight on the high traction wheels. But the center of mass is simply that point where you could consider the whole weight of the robot to be acting. So for instance, if we look at this this situation over here, if the center of mass is over here and the wheel is touching the ground over here, well, you can see that's just going to fall over. So in other words, wherever those points of contact are on the wheels, the center of mass needs to be in between those points, otherwise it's going to tip over. So if you had, driving both the front and the rear wheels, then this would be a good center of mass location. This is obviously is bad. This one isn't good because it's so high, and this one is okay, because on this particular robot you have your high traction wheels on this end and your slippery wheels over here, so you want to get the weight more over the high traction wheels. Okay, so here's another case where you have your center of mass is over the high traction wheels in this one. This one again, too high. This one right here, you have a high traction wheel here and the slippery wheel here. Center of mass is too close to the slippery wheel. This is where your drive wheels are, so you want that closer over here. And in this particular case, this would be where you might have some casters on either end and drive wheels in the center. So again, you want the center of mass right over that drive wheel. Okay, and if you're going up a hill, of course, then that center of mass, the weight is pointing down through the center of mass. It could shift to outside your wheels, especially if the center of mass is high. So, and then in terms of the gearing on your robot, it's not likely for this experience that you're going to get initially here that you're going to have a multiple speed transmission. So you have to there's going to be trade-offs. If you gear your robot so that it goes really fast, well, it's probably going to be harder to control, and you're not going to have a lot of torque if you have to pull something or push on something. So there's kind of a trade-off, and they're inversely related. If you gear your robot so that it's fast, then there's not going to be as much torque on the wheels. And if you've ever rode like a 10-speed bike or something like that, you know that if you're going up a hill, you're going to want to be in a low gear so that you get more torque. Coming down a hill, you want to be in a high gear because you don't need as much torque. So a general rule of thumb is you want to do a design so that if for some reason the robot is blocked, that you'll have enough torque to spin the tires. Because if you go to full voltage on your wheels, on your motors, and the wheels are not slipping, they're just stuck, then your motors will heat up very quickly and you can damage the motors. So that's kind of just a general rule of thumb. Another concept here is wheelbase and wheel track. So wheelbase is the distance between your axles, and your wheel track is the distance between the wheels side to side. So this ratio can be important in terms of how easy it is to turn. A robot with a long wheelbase compared to the wheel track, well, it will go straight more easily, but it's going to be harder to turn. Later on, when we do force analysis, we'll talk about why that's true. And we'll have to stop here and pick up from the next video.